Good morning everybody. In this video, I discuss about the network theorems. Network is a combination of various components such as resistors, capacitors, inductors, current sources, voltage sources are interconnected in all sorts of manner. That means all sorts of manner means either they may be connected in series or they may be connected in parallel. Most of the networks cannot be solved just by applying a basic laws such as series combination of resistances and a parallel combination of resistances. Usually linear circuits can be solved just by applying a Ohm's law. The complex networks can be solved by applying Kirchhoff's laws. But in some complex networks, applying Kirchhoff's laws becomes lengthy and tedious. To make the calculation easy, a number of network theorems have been formulated. They are Thevenin's theorem, Norton's theorem, superposition theorem, maximum power transfer theorem, and the reciprocity theorem. To analyze these theorems, one should have a knowledge about the Ohm's law, Kirchhoff's law, and branch currents. These we have already learnt in our basic classes. But still, I would like to just recollect these laws before going to the discussion of the theorems. So in this video, I am just describing a Thevenin's theorem, and the statement of the theorem I will discuss in this video, and also how to Thevenize a given network I am discussing, and the remaining theorems I would like to explain in my next video. Okay, so first let us try to recollect the basic laws what we have already learnt in the PU classes. Okay, so let me give the information about the Ohm's law, and we know that already Ohm's law states that when a current through the conductor is directly proportional to the potential difference between its ends, provided temperature and other physical conditions remains unaltered. Mathematically, the Ohm's law can be expressed as V is equal to IR, where R is known as proportionality constant known as resistance of a given conductor. Okay, so next we shall try to recollect the Kirchhoff's laws. Kirchhoff, in order to analyze a network, he introduced two laws. The first law is also known as current law, and the second law is also known as voltage law. So the current law states that the algebraic sum of the currents at a node, so this is the point, this point A is known as node. The algebraic sum of the currents at a node in an electrical network is 0. That means the amount of currents entering the node or a junction is exactly equal to amount of currents leaving the junction. Okay, so when the network is in the form of a loop or a mesh like this, we can apply a voltage law. So if the circuit consists of more than one source of EMFs and number of resistors, then we can make use of a Kirchhoff's voltage law to analyze the this type of network. And the statement is the algebraic sum of the in a loop or a network or mesh we can say here. So the algebraic sum of the EMFs is exactly equal to the algebraic sum of the product of current and resistance of the different part of the loop. Okay, so this is all about Kirchhoff's first law and the second law. So sometimes we make use of branch current equation also in solving the theorems, especially in solving Norton's theorem we are going to use this branch current. So I am giving a little bit information about branch current also. So whenever the current is flowing in a branches like this, okay, So the main current is going to, if it is entering into the two branches, it divides into two currents as I1 and I2. So we can calculate these branch currents using a simple formula as that the branch current is equal to main current into resistance of the other branch divided by total resistance of the circuit. So if I need to calculate the branch current I1, so using this formula, I can write the equation as main current is I, okay. Resistance of the other branch is R2 because I am calculating a current in this branch, okay. So I1 is equal to main current, okay, I into resistance of the another branch is R2 divided by total resistance of the circuit is nothing but R1 plus R2. Similarly, I can calculate I2 as main current I into resistance of the another branch is R1 divided by R1 plus R2. So this is about your branch current. Now let us discuss about the Thevenin's theorem. So the Thevenin's theorem was first formulated by Helmholtz. Later it was modified by Charles Thevenin in the year 1883. Okay, so this theorem is very useful when we desire to know the amount of power, current or voltage drop in a particular component of a given network. So the statement of the theorem I have given here, okay. So the DC statement and AC statement both I have given, as this theorem is applicable for both alternating current as well as the direct current. So let me give the statement of the DC current. So that is the network consisting of a DC source of EMF, okay. So any two terminal linear bilateral network consisting of a several fixed resistances and a voltage source can be replaced by an equivalent circuit consisting of single voltage source known as Thevenin, okay, and it should be connected in series with a single resistance known as Thevenin, Thevenin's resistance, okay. So AC statement is just similar to DC statement, just we have to replace wherever the resistance is there, that has to be replaced with the word impedances. So instead of writing Thevenin, the notation used in AC circuits are Z Thevenin. Impedance is denoted by letter Z, so it is replaced with the Z Thevenin here. So now let us try to understand how to Thevenize a given circuit. That means if the circuit is consisting of a several resistances and a voltage source, we can draw or construct a single circuit or an equivalent circuit consisting of single resistance and a voltage source, and these two must be connected in series with each other, okay. So let us look into the circuit and try to Thevenize a given circuit here. So this is the given two terminal network, okay. So in order to Thevenize this circuit, we need to follow few steps here. The very first step what we have to do here is we have to disconnect a load resistance between the terminals A and B, okay. So the first point what we have to do, we have to disconnect the load resistance from the terminals A and B. Secondly, what we have to do is we have to determine open circuit voltage across the terminals A and B. Okay, open circuit voltage is just nothing but your Thevenin's voltage. And thirdly, what we have to do is we have to determine the Thevenin's resistance. To determine the Thevenin's resistance, we have to remove this voltage source and replace this voltage source with its internal resistance. Okay, then we have to determine the Thevenin's resistance. And the next, after getting a Thevenin's resistance and Thevenin's voltage, we can construct a Thevenin's equivalent circuit such a way that the Thevenin voltage source must be connected in series with the Thevenin's resistance. Finally, what the last point what we have to do is we have to connect back. So in the beginning we have disconnected this load resistance. So the final step what we have to do is we have to connect back the load resistance between the terminals A and B. So this is the simplest circuit the two-terminal network reduces to a Thevenin equivalent circuit. Then making use of this circuit, we can calculate the current through the load resistance or even the voltage drop across the load resistance. Okay. So the current through the load resistance can be calculated using the formula just I is equal to EMF divided by total resistance of the circuit, that is EMF in place of EMF what we have V Thevenin. Okay. So the current through the load resistance IL can be calculated using the formula V Thevenin divided by R Thevenin plus RL. Similarly, voltage drop across the load resistance can be calculated using the formula IL into RL. Okay. So this I have listed here, that is IL is equal to V Thevenin divided by R Thevenin plus RL. VL is equal to IL into RL. Since IL is equal to this value, just replace it. The final expression for load resistance comes out to be this one. So making use of these two formulas, you can calculate the current through load resistance as well as voltage across the load resistance. Now we will try to understand how to Thevenize a circuit with by solving one problem here. Okay. So just the problem is like this: find the Thevenin equivalent circuit for the following circuit. So this is the given circuit. Okay. So this is your two-terminal given network. So we will follow the steps one after the other here. The first what we have to do, so let me repeat the points quickly once again. First, to begin with, what we will do, we have to disconnect the load resistance. The second point what we have to do, we have to determine a open circuit voltage known as Thevenin voltage across the terminals A and B. So in the third step what we have to do, we have to replace this voltage source with the internal resistance. Then we have to determine the Thevenin resistance between the terminals A and B. Finally, we have to construct, after getting V Thevenin and R Thevenin, we have to construct an equivalent circuit. So first I will disconnect this. My circuit reduces to this form. So we have to determine the Thevenin voltage between the terminals A and B. So to determine Thevenin voltage, we need a current, because voltage is equal to I into R. Okay. So first we have to calculate a current through this branch, as the current will flow only through this branch here. It will not enter into this branch because it is a open circuit now. So to calculate I, what we have to do, EMF divided by total resistance, that is 36 ohms divided by total resistance is 3 plus 6. So it comes out to be 4 amperes. So V Thevenin is equal to I into, across this resistance we have to calculate a Thevenin voltage. Okay. So 4 amperes into 6 ohms will give you the Thevenin voltage. Okay. That is I into 6, that is 4 into 6 is equal to 24 volts. So we have calculated a Thevenin voltage. Now we need to calculate Thevenin resistance. To calculate Thevenin resistance, remove this voltage source and just replace it with its internal resistance. Now we have to look into the circuit from this point, that is between across the terminal A and B, we need to calculate a Thevenin resistance. So from this circuit, it is clear that this 4 ohm resistor is in series with the parallel combination of 3 ohm resistor and a 6 ohm resistor. Is it clear? So 4 ohm resistor is in series with the parallel combination of 3 ohm resistor and a 6 ohm resistor. So R Thevenin, what we have to write here, 4 plus, okay, and we know that whenever resistances are in series, the equivalent resistance is given by R is equal to R1 plus R2, etc. Okay. So making use of that series and a parallel resistance combinations, let me write the equation as R Thevenin is equal to 4 plus 3 into 6 R divided by 6 plus 3. Okay. So if you do the calculation, you will get 6 ohms as the Thevenin resistance. Now you have to draw the equivalent circuit consisting of Thevenin voltage in series with the Thevenin resistance. Now you say Thevenin voltage, how much we have got? 24 volts. And so in place of Thevenin voltage, you write a 24 volts. Okay. And Thevenin resistance is 6 ohms. So you just connect a 6 ohm resistance in series with the Thevenin voltage. Finally, what we have to do? Connect back the load resistance. Okay. So this completes our problem. That is, the problem is asked to determine the Thevenin's equivalent circuit for the given network. So this is a Thevenin's equivalent circuit for this given network. So in this way, so the Thevenin's theorem, that is a given network, two-terminal network, can be reduced to its simplest form, making use of a Thevenin's theorem. So the remaining theorems I will discuss in my next video. Thank you.